Now let's do a slotted line example. This is example 2-5 out of your book on page 60. Let's suppose that we're given the characteristic impedance, the standing wave ratio, and the location of the minimum of the wave. What we'd like to find is the load on our line. So the first thing that I need to do is be able to find Lmin in terms of wavelengths. So I'm going to take Lmin, which is 12 centimeters, and I'm going to divide it by 0.6 meters, which is the wavelength, and that gives me 0.2 wavelengths. So that's my Lmin. Now I'm going to plot my standing wave ratio, which has a magnitude of 3. So there's my S value, and I know that Lmin is going to be 0.2 wavelengths away from my load. So my Lmin is over here on this side. Lmax was on this side. So rather than drawing the complete standing wave circle, because I don't have a protractor on me right now, rather than drawing the complete circle, I'm just going to measure my length right here onto a piece of paper, as I've done so many times, and I'm going to effectively rotate that around to here, draw it on this side. So my Lmin point is right there. There's the Lmin. Now I know that Lmin is 0.2 wavelengths away from my load, so I'm going to have to go from this point A, which is right there, towards the load, not towards the generator. Right here, this is a little line that says go towards the generator. Here's a little line that says go towards the load, this direction. So if I read my value right here, which is 0.5 wavelengths, I know that I need to go 0.2 wavelengths towards the load. So 0.5 minus 0.2 is going to be 0.3 wavelengths. So come on out here, 0.4, 0.38, 37, 36, 33, 32, right there, the point where I want to go. So I'm going to draw a dashed line from the 0.3 to the center of the Smith chart, like this. And then I'm going to use the magnitude that I had before, and I'm going to plot it on that line. So it's as if I went from point A to point B, which is my load. I went 0.2 wavelengths towards the load, and that is going to give me my ZL value. So let's read it. ZL is going to be equal to a real part right here. Looks like that's about 1.8. A real part of 1.8. The imaginary part's negative because it's on the bottom. Let's follow that out here. That looks like about 1.3 minus J 1.3. To denormalize it, we need to multiply this by 50 ohms. And that gives us 90 minus J, let's multiply 1.3 times 50, 65 ohms. And that is my load. Now let's compare that to what the book got as their exact answer. In the book, they say that ZL is equal to 85 minus J 67 ohms. That's pretty close to what I got. Why would I be off a little? Because when I go to read my real and imaginary values, they may not be exact. So this is about as close as you can expect to get with a Smith chart. So the example that we just did, we could call a slotted line example. That's what happens when you want to find the load impedance when you are given the location of a minimum or the location of a maximum. In this example, I showed you what to do if you knew the location of a voltage minimum. If you knew the location of the voltage maximum instead, let me just get a red pen for that. If you happen to know Lmax instead, such as this value right here, you would still rotate towards the load, whatever distance it was, until you were to reach it. And then you'd find your load over here someplace.